Good morning and welcome back to the TV studio here at the International RFID Congress in Marseille. And to start the afternoon, we have the chance to have Amir Kotb, and sorry if I butchered your name, Amir.
Thank you.
From the University of Liverpool. And he's going to introduce us to an RF parking solution, smart parking. And before we see some pictures of that solution, Amir, why the University of Liverpool is interested in smart parking?
University of Liverpool is interested in a lot of things. So one of them is smart parking. It's a research project, and I'm a PhD student working on this project.
Okay, it makes sense. Go ahead, show us your slides, and then we'll answer questions.
Thank you. So good afternoon. My name is Amir Kotb, and I came from the University of Liverpool, from the Electrical Engineering Department. Today I'm going to talk about one of our recent work in the domain of smart car parking, and it's called RF Park. It's a new solution using passive RFID systems. It's a parking spot occupancy detection system. In this presentation I will speak quickly about the problems that we are facing in because of parking, and what are the systems right now and the sensors used in them. Then I will talk about the RF Park and show you some experimental analysis, followed by a pilot study in our university. So let's get started. Nowadays there are more than 1.2 billion cars making a lot of traffic congestion. A car is parked for more than 95% of its lifetime. This is less in the UK, where it is parked for 8,500 hours a year, making 90%. 30% of traffic is due to cruising for parking. And if we take France as an example, we will find out that 70 million hours are spent for searching for parking per year. In order to overcome these problems, smart parking systems must be developed, and the sensors used in them are, for example, acoustic sensors, piezoelectric, loop detectors, magnetic sensors. The most common ones are the ultrasonic and the infrared, and they work in the same way by transmitting waves at certain times. There must be synchronization of time. And when the signal is received back to the sensor, they calculate the time difference of arrival, calculate the distance, and so on. Each of those sensors have their own shortfalls, which I will talk about later, but let me first say also we have the image-based technologies, which use the computer algorithms to detect the spot detection. As I said, all of them have their own limitations. For example, the sensors they require complex installation, maintenance. They are sensitive to weather conditions, sensitive to pressure, and they all need power. As for the image-based, they are expensive in terms of computing. They require calibration. They are sensitive to light intensity, weather conditions also, and they are expensive for indoors. So moving on to RF Park. So RF Park is different than all these sensors, and it overcomes their limitations. It's not sensitive to weather conditions. They are passive, so they don't require any batteries or power lines. So looking at this figure, we will find the architecture of the system. There is on the left bottom side the parking lot with RFID tags. So we deploy first the passive devices on the ground. Each parking spot will take a passive tag. Then an array of RFID reader antennas are deployed around the parking area to interrogate the tags all the time and send reports to the base station. The base station will then check which tags are red and which tags are not. The red tags imply that this parking spot is vacant. otherwise it is occupied. And this is how the detection system works actually. On the right side there's system planner where we prepare the project for this parking area. We answer the layout plans, and then with some simple setup we prepare a digital map which is then inserted to the database and compared afterwards with the reports from the RFID readers. In this figure we show a simple implementation, and we show also the devices that we have used. From the reader side we used Impinj Speedway reader along with a layered 8 dBi antenna which has a 70 degrees beam width. For the tag we used the Omni ID ultra passive tag. Using this combination we got around 27 meters. So this setup, the distance between the antenna and the tag is more than 25 meters actually. We can cover, with this setup, we can cover around 8 parking spots. So in order to further analyze this, we installed only one tag, and then we started to plot the RSSI versus time. In the parking process, it starts when the parking spot is free, and then car is entering, and then parking stop, car leaving, and so on. From the figure we can see that the received signal strength is at -64 dBm when the spot is vacant. Then when a car starts to enter the parking area, the RSI increases by around 8 dBs. Then when the car just stop over the tag and cover it completely, I mean parked in the parked state, there is no any received signal strength at all. And here we detect that a car has parked. This figure shows a simple analysis also when we place a tag in a vacant spot and we place 2 cars around, or 3 cars, or 1 car on the sides to check the received signal strength, and we found out that there's no attenuation of the signal because of the surrounding cars. Next we deployed the system in a real parking environment and simulated what will happen in a parking environment. Typically people are going to move around and cars are going to pass around, and so they will cut the line of sight between the antenna and the tag. And this what actually we saw in the results. Anytime at position 2, if you can see that in the figure, at position 2 where exactly the car stops in front of the tag and break the line of sight, there's no received signal at all at this time. In order to solve this limitation, we adopted the observation time window technique, where we interrogate the tag for a certain period of time, for example 10 seconds. During this 10 seconds we make sure that whenever cars has passed, they will take less than 10 seconds, of course, so at least the tag will be read once. So if the spot is vacant, it will after 10 seconds will be shown in the system as vacant. And there's a table shows if we didn't use or if we used very small observation time, we get around 76% of false detections, whereas when it's 15 seconds we don't get any false detections at all. Here we show a real pilot study in the university with 6 tags on the site, and we ran this for 2 consecutive weeks. And as you know, the weather of UK is not that good, so it rains a lot. So during that 2 weeks, a lot of weather settings has been simulated, and we can say that after the 2 weeks we got 100% detection accuracy in a normal parking environment. We also installed some CCTV camera to monitor the area during the experiment to verify this result. And we also implemented that by developing an Android application and Windows application to show the parking spaces to the user. The ones in red are the spots that are occupied, the ones in green are the spots that are vacant. And that's it. So to conclude this, we say that the parking problems are very critical. Sensor technology still has their own limitations, and that's why we propose RFPark to tackle those. Thank you very much.
Thank you, Amir. I had 3 questions, and you answered pretty much the two first ones, but I'll still ask them, and then we'll move to the third one, which you didn't answer. So what would you clarify as the originality of RF Park? What's original? And I can say no calibration, no energy at the tag level. Is there anything else which is different from other systems?
When we talk about originality, we want to say that it's the first time that someone do actually this work. So here in this RFID Congress, at least I didn't see that.
Oh, it's original in RFID, but it's, parking, I mean, automatic system parking is not new. It's like, what's original versus other technical solution to do so? That was more my questions. But that's why I answer, part of it is no calibration, so easier setup, no change of batteries of any kind. Because are you going to put the tags within the concrete, within the road itself, the parking? When they're over the top?
Over the ground, over the top. So it will just be fitted with some screws. It will need a very simple method for this.
All right. Second question, well, that was the second question. Well, the difference between other car parking detections, and you answer very clearly during your presentation. The third one is more the future plan. I mean, okay, this is an experiment within university. Do you have plans to build that in the UK, some other places? Yeah.
Yeah, at the moment we have proved the concept, but in the later stage we would like to develop our own reader system and the tag itself. At the moment the tag, as I say, this covers 27 meters, but we can develop our own tag and our own antennas that can make a very much big range. Another thing to do is to just use rotary machines to rotate one antenna of the reader 360 degrees and use very high gain antennas with a very small beam width, such that we can cover a real big parking space. Yeah.
Okay. Well, thank you very much. Good luck with that project. I hope you'll be successful and you'll be able to implement it in real life. And thank you for explaining that parking system to us.
Thank you very much. Thank you.
Thanks, Amir.